Hi friends, welcome back to another video. And today we will be extending our discussion on the topic of continuous functions. Previously, we spoke about continuity at a particular point, relating it to limits, right? So we said that a function f is continuous at a particular point, say C, if and only if, number one, the limit as x tends to C, it exists. It exists. That means the left-hand limit at C should be equal to the right-hand limit at C. Okay, that's number one. And number two, this limit is nothing else but the functional value at this point C. That is limit x tends to C, fx is nothing but fc. And that would give you the essence of continuity at a particular point. Now, continuity is a very important topic. It's a very important concept in maths, and it's applied at various levels, be it physics, be it economics. It can be applied in a lot many ways because discontinuities are very important to study. Whenever there is a discontinuity, there is some change happening. It might be associated to behavior. It might be associated to, say, voltage. It can be associated to different various things. And that's why continuity is important. Talking about continuity at a particular point, we can take it forward and talk about continuity in particular intervals. Now, you can have two kinds of intervals. You can have an open interval. You can have closed interval. Starting with the open interval. What would it mean for fx to be continuous in an open interval AB? An open interval does not contain the endpoints. It just contains the points in between AB, right? So continuity would mean that the function should be continuous at each and every number which comes in between AB. So if f is continuous at each point which belongs to or which is in this interval open AB, then we would say that f is continuous in this interval AB. Okay. Now, AB could be anything. It could be infinity. It could be some finite number. It could be anything. So the same definition will be applied to in case it's the interval A to say plus infinity. In case it is the interval say minus infinity to B. In case the interval is minus infinity to infinity. And when a function is continuous at every point in minus infinity to infinity, we say that the function is continuous everywhere. So whenever you are asked a question, is function fx, whatever is given to you, continuous everywhere? You would be looking at from minus infinity to infinity, that is the entire set of real numbers, is your function continuous there? Now notice something, the definition of continuity, the definition itself, it involves double-sided limits. It involves two-sided limits, right? The left-hand limit is equal to the right-hand limit, and that is equal to the functional value. Now, the intervals like open AB, minus infinity to B, or A to plus infinity, these intervals do not include their endpoints, right? How to define at endpoints the concept of continuity? How to define the concept of continuity in intervals like closed AB or closed from one side and open from the other? How would we define continuity at this level to these kind of intervals? Well, now notice that when you have a closed interval, suppose this interval is closed at A. Now, whatever is on the left of A, it's not a part of my interval. I don't have to be bothered about it. I don't need to know what the function looks like there because the function is not going there at all. It's not a part of our domain, right? So therefore, to remedy this problem at the endpoints, what we can do is that we just talk about one-sided limits at the endpoints. What essentially it means that a function is continuous at an endpoint of an interval if its value at the endpoint is equal to the appropriate one-sided limit at the endpoint. Meaning hereby, so for example, look at this graph from A to B. What's happening here is the function is continuous completely in between. At the endpoints, if you notice, at the endpoint, we would be interested in what is happening from the left of B, the left-hand limit at B. The left-hand limit at B of fx, which we basically write as limit x tends to b minus, that is clearly f of b. That is clearly f of b. But if you look at the right-hand limit at a of this function fx, that is something that we write down as x tends to a plus fx, that is not equal to f of a because f of a is somewhere out here, as you can see. So which means that this function is continuous at b, at the endpoint b, but it's not continuous at the endpoint a. So in general, at an endpoint, how do we define continuity? We make use of one-sided limit. So there are two terminologies that we generally use here: continuous from the right and continuous from the left. So when a function is continuous from the right at, say, a particular point C, what's happening there? The limit, since we are saying right, so the right-hand limit, that is x tends to C plus fx, is actually equal to the functional value at C. So therefore, it's right continuous or continuous from the right at C. When it is continuous from the left at, say, C, basically what we mean to say is that the limit as x tends to C minus fx is equal to fc, and that would mean left continuous. So let's now define what is continuity on a closed interval AB. So a function is said to be continuous on a closed interval AB if the following three conditions hold. And what are these three conditions? Number one, f is continuous at all the points in between AB. So that means it is continuous in open interval AB. That's the first thing. So it should be continuous on the open interval AB. Number two. So what is happening is that we are moving from A to B. So we are not bothered on the left of A and we're not bothered on the right of B. That means the function should be is continuous from the right at C, at A. And number three, f is, it should be for continuity in closed interval AB, it should be continuous from the left at B. And this will give us continuity on the closed interval AB, okay? Let's work on a couple of questions in order to understand if we have figured out what exactly continuity is. So let's talk about continuity of the following functions. Number one, if fx is equal to square root of 9 minus x squared, what can you say about continuity of this function? So Nothing has been provided to me about the domain. Where would this function lie? Okay, what is the domain? What are the values of x's that I should take? That's the first thing that you must observe here. So we should be talking here about the domain first of all. Now, this function would be a well-defined function when whatever is inside the square root is positive, right? So therefore, 9 is greater than or equal to x square, or in other words, x square is less than or equal to 9. And that will only happen when x is in between -3 and 3. Okay? So that means domain of this function is -3 to 3. Is this function continuous on this domain? Well, yes, it is. Number one, you can create a graph for this. Then also you will figure it out. Number two, you can think about in terms of the limits. It's easy to see that, it's just going to be a semicircle from -3 to 3, right? It is just fx is square root of 9 minus x square. In other words, y is this, which basically means that y square is 9 minus x square, or x square plus y square is equal to 9. And you have the positive square root. So it's going to be all y's are positive. So you will just take the semicircle from -3 to 3. Clearly, graphically, it is a continuous case. Apart from that, what you can observe? You can observe, first of all, there are three conditions for continuity in closed interval. The first condition is open interval. So, number one, for any c belonging to open interval -3 to 3, is the function continuous at c? Well, yes, of course it is. If you take the limit as x tends to c of fx, it's going to be the limit as x tends to c of square root of 9 minus x square. And since c belongs to open interval -3 to 3, the function is well defined at this value c, and hence you will get square root of 9 minus c square, and it is nothing but fc. So, well, the function is continuous for every c in the open interval -3 to 3. The second case that we wish to see is at the endpoints, right? So we would be interested in looking at the limit as x tends to -3, right-hand limit at -3. So -3 plus fx. And that's going to be the limit as x tends to -3 plus square root of 9 minus x square, which very much exists. Why? Because the interval starts from -3. -3 is the value that I can put here. And the moment I'll do that, I'll get the value of the function at -3, which is 0. Okay? And the same thing, we are interested in figuring out the limit at 3, but not two-sided, only one-sided, which is the left-hand limit. So we are interested at 3 minus, that is the left-hand limit at 3 of fx, which will be equal to limit x tends to 3 minus of square root of 9 minus x square. Again, the function exists at this point, and the moment you will put 3 minus is almost 3 there, you will get again the value which is the value you will get at 3 also, which is 0. So clearly what is happening here? It is right continuous at -3, left continuous at 3, and continuous at every point in between. Hence, it is a continuous function where it is continuous in between -3 to 3, including the endpoints, that is closed interval -3 to 3. So, of course, you should also concentrate on what the domain for the function is. I will not say here that it's continuous everywhere. The function only exists between -3 and 3. So, you cannot talk about the entire R. Okay? Be cautious of that. Next, let's talk about the general properties that you must always keep in your mind when two functions are continuous at a particular point C. What all consequences do we have to that? The consequences of that, number one, the sum of two continuous functions will always be continuous. So if f and g, they're continuous, then f plus g is continuous for sure at C. The difference is also continuous. See, continuity simply means that there is no break. So if there is no break in f and g, you add and subtract, you will never get a break. The product is also continuous because again, since there is no break, there will be no break for the product as well. And so as for the quotient. But I'm sure you have it in your mind that how can we have no condition for the quotient? We have a denominator here. Yes, the denominator should not be 0 at C, right? So, or in other words, we can say that this is only possible if G of C is not equal to 0. Okay, so this is something in which you should keep in mind. And you can also say that and f by G has a discontinuity at C if G of C is equal to 0. The moment your denominator will be 0, you will get a point of discontinuity there. Okay. So these are the properties associated to two continuous functions. With these, keeping these properties in your mind, you can actually easily talk about polynomial functions and rational functions, the continuity around it. Are they continuous? Well, a polynomial function, in general, you must have heard it, that polynomial functions are always continuous. Why is that happening? That is coming from the concept of limits. We have already seen in limits how we can find out the limit for, at every point for a polynomial function. Suppose Px is any polynomial function and A is any arbitrary point. So if you see the limit as x tends to A of this function Px, it will always be equal to Pa because it's a polynomial function. You can just, put the value of x and get the limit, right? You just need to substitute. And this is the reason why a polynomial function will always be continuous. It is always continuous in nature. And so as the rational functions, because rational functions are nothing but they are the quotient form of a polynomial function. When you divide one polynomial function by another, it's a rational function. The only problem there will be the fourth property that we've just seen. You will have a discontinuity the moment your denominator becomes 0 or the limit of that denominator becomes 0. Then you will have a problem. So quoting it formally, a polynomial function is continuous everywhere. Number 2, a rational function is continuous at every point where the denominator is non-zero. And it will have points of discontinuities whenever your denominator is 0. Let's understand it using an example. Suppose you have y equals to x square minus 9 upon x square minus 5x plus 6. For what values of x is there a discontinuity in the graph of this function? Well, if you remember in continuous functions, I always keep on saying that, and I'll repeat it today itself, that continuity is a graphical concept. Your graph is, it looks continuous. When you start graphing or you pick up your pen to draw something and there is no break, that is continuity. So it's a graphical concept per se. So that's why it's not necessary that you have to graph this function in order to check it, but it's a graphical concept. So here, if I'm asked this question, what are the points of discontinuity? I know that this is a rational function. I know that the points where I will have discontinuity are the points where my denominator becomes 0. That will create a problem. So your x square minus 5x plus 6, you can factor it out and you will see that x minus 2, x minus 3, these are the two factors. When is it equal to 0? It is equal to 0 when x is 2 and 3. So you have 2 points of discontinuity in the graph of this function. You can very well graph it, you will figure out. At 2 and 3, you will face discontinuity. Okay? On the other hand, let's look at the graph of or the function modulus of x. Modulus x, is it continuous everywhere? Or do we have a point of discontinuity here? Well, to understand it, modulus x looks like just x when x is greater than 0. It is 0 when x is equal to 0. It is minus x when x is less than 0. And hence, we have graphed it many times before. When you will graph it, at 0, you are here. When x is positive, that is, x is somewhere here, your y is equal to x. So the line y equals to x goes like this. When x is negative, that is, it's here. What will happen? Your y is equal to minus x. Now, minus of minus, since x is less than 0. So minus x would basically be greater than 0. So it will give you a positive value, which is quantity-wise same as x. So this is the graph of modulus of x. Do you think we had to break ourselves somewhere? If you would have a pencil in your hand, you can just, the way you write V, it's a V graph. You did not stop anywhere. There is no break. It is continuous whatsoever. The only point of concern was 0 actually. Everywhere else, we don't have any issue. And at 0, limit as x tends to 0 minus, limit as x tends to 0 minus of fx is basically minus x, which is 0. Limit as x tends to 0 plus of fx is positive side of x. So x, now x you will put 0, you will get 0. And f of 0 is equal to 0. So that means the left-hand limit is equal to the right-hand limit. It is equal to the value of the function at 0, right? So hence it is continuous. Everywhere we would say it is continuous everywhere. The only point of concern was x equal to 0, and there also it is continuous. That's why modulus graphs are always continuous. So you take modulus of any function, you will find out that modulus graphs are always continuous in nature. Well, this is what I wanted to discuss in this lecture. Thank you very much for watching.